In her dim laboratory, Krish, a renowned scientist, worked intently on a new chemical formula. But a sudden slip sent a vial crashing to the floor, splashing its glowing contents onto her. Her body trembled as the transformation began.
Oh my god, what are those freaks?
How did they turn into zombies? I don't know. I'm scared.
Isn't that the famous scientist's house? Let's go! Dr. Krish? Dr. Krish?
Her house is big. Let's explore her rooms. Maybe she's busy.
I think they got infected.
Well, there goes our chance to save this one big of a mess.
Whatever. If you can't find a cure, let's at least find an exit out of this room without dying.
Guys, there's a laptop.
I'm scared. How can we make it out alive? Let's not lose hope. We will just need to find a way to get out of this house. This is it. This is the room one. The document says the first clue is hidden in this room.
Oh no! Dr. Krish!
Stay calm, guys. We need to use our minds for this. She's testing us. She's using math against us.
Mathematics plays a vital role in understanding how diseases spread, estimating infection risk, and measuring the success of cures or vaccines. During real epidemics, scientists use probability, sequences, and data analysis to predict how fast a virus will spread and how effective a treatment will be.
Yeah, mathematical modeling was heavily used during COVID-19 to estimate case growth, infection risk, and vaccine effectiveness. The World Health, WHO, and the Department of Health, DOH, rely on these models to guide decisions on lockdowns, vaccine distribution, and prevention measures.
No, she's teaching us. Look, this is probability. She used this to model how likely her virus is to infect someone.
Explain it to us like we're in class. Fast class.
Okay, so hypothetically, there are humans here who had a 12% chance of exposure per hour. They were inside for 3 hours. Now, instead of calculating the chance that someone got infected, we calculate the chance that nobody did.
That sounds backward.
It's actually easier. It's called the complement rule. Probability of at least one infected equals 1 minus non-infected because non-infected is the simplest scenario. Step 1. Find the chance of not being infected per hour.
So in any 1 hour, each of us had an 88% chance of staying safe. Ah, okay, so far so good.
Step 2. Extend that to 3 hours.
That means each of us has a 68.1% chance of being safe the whole time. That's not super comforting.
Now, the important part, we want the chance that all 5 of us were safe.
Step 3. Probability all 5 are safe.
So, only 14.8 chance none of us are infected?
Yes, so the chance that someone was infected is
1 minus 0.148
equals 0.852. Which means 85.2%.
Correct. Room 1 complete.
Run!
He's modeling the infection like a real epidemic.
Yes, this is classic exponential growth. When something spread by doubling, the numbers rise ridiculously fast.
Teach mode, Angela. We're dying and learning.
When infections double, every fixed time of the use, n equals n sub 0 times 2 raised to the power of p. N sub 0 is the initial number of people infected. P is the number of times the population doubles, and 2 raised to the power of p is how many times the infection has doubled. What's our data? 20 initial zombies, doubling every 6 hours. Predict the number in 24 hours.
First step, find how many doubling periods fit into 24 hours.
So that's 4 doublings.
Meaning, it multiplies by 2 4 times.
Exactly.
So mathematically, if we start with 20 and it doubles every 6 hours, then after 24 hours, it is 20 times 2 raised to 4 is equals to 20 times 16 is equals to 320. That's how exponential growth works. Slow start, terrifying finish.
Correct. Room 2 complete.
Should we go into the last room? The documents of the final problem is inside the lab where the virus began. But where is that lab though? We've almost searched everything.
Wait, what if the lab isn't a room number? What if it's
The restricted area, the one with the wooden door.
That would make sense. This must be it.
Why did it open for us? Unless someone opened it earlier today.
Trial?
Don't tell me.
No way. Dr. Krish was the one who made the virus. That explains everything. She knows the layout, she knows the security. And she kept chasing us because
Because she doesn't want us to find the cure.
hurry, we have to solve the problem now.
Each cure vial has a 70% success rate. You must inject exactly 3 doses. What is the probability that at least 1 dose works?
Okay, teaching mode, guys. If we solve this wrong, we're dead. So let's explain properly.
Let's think. At least one works is the opposite of non-work.
Right, and mathematically, it's easier to calculate the probability that all 3 fail than subtract from 1. Exactly! It is called the complement rule. P sub W is equal to 1 minus P sub N. If each dose has a 70% chance to work, then the chance it fails is 30% or 0.3. So, P sub N is equals to 0.3 times 0.3 times 0.3 equals 0.027.
Using the complement rule, P sub W equals 1 minus P sub N, then substitute the number P sub W equals 1 minus 0.027 is equal to 0.973.
So, the cure has a 97.3% chance of working if we inject all 3.
Then hurry! We have a high chance. Let's use it.
Inject it now!
Correct. Final room complete. You have found the cure.